In this video, we continue showing you some more fractals. In the last video, we talked about spiral. Here we're going to talk about spiral motions that produces some interesting figures that we're going to call whirls. And then we're going to move on to more fractal trees and present some examples of fractal stars. Let's get started. This is the worksheet for WHIRL, in which we have two arguments in the function. This is the function as I translated it from BASIC to SMath Studio's the programming language. And P represents the number of size of a polygon, and then N, that polygon gets twisted and reduced by an N number of times. For example, P equals 4 and equals 40. We're going to see some of the examples pretty soon. This is the function that does that, and basically we have an angle A, which is related to the number of twists and pi, a reduction factor related to the angle A, and an angle B, which is 0.05, and then we produce different angles. This angle T gets evaluated, and then the x and y coordinates corresponding to a radius 1 with that angle. It's the first element in the graphic, and then different values are created providing the corners of the modified and reduced figure. For example, by the way, as I mentioned, P is the number of sizes of the polygon, and N is the number of twirls. So here's 3 with 30, 4 with 40, 5 with 50, 6 with 60, 7 with 70, 8 with 80, 4 with 80, 10 with 100, and so on. And you can download these and change anything you want. If you want to have a polygon of 12 size, for example, and make it twirl 80 times, then the data will be produced and it will give you these. Alright, so that's the first example that I wanted to present. This is not necessarily a fractal. It's just a nice looking figure obtained by rotating and reducing the original figure of with as a regular polygon. In the next example, we're going to see the Pythagorean tree. The Pythagorean tree is available in Lewis' book, page 63, figure 411. It does have a lot of calculations presented in here, and again I just translated them from a BASIC. And basically what we have is this figure. I'm going to reduce this a little bit. Okay, so this figure gets twisted and reduced in a symmetric way, and so if I'm going to reduce a little bit more so we can get the whole picture in here. If I change the parameter P, which is the main parameter here, this is just the level of the fractal, then you're going to see how the tree starts developing with 2 branches, 4 branches in the third step. Now we get 1, 2, 3, 4, 5, 6, 8, and it's doubling in number with the increase in value of P. 16. I'm going to drag it down a little bit. 6, and so on. I have here the case for 8, which I took a screenshot out of it because it takes a while to produce, and even for 10, and it produces this nice fractal tree called the Pythagorean tree. And the reason why it's called Pythagorean is because it starts with the simple triangle, and then you build upon the size of that rectangular triangle. That is the second example I wanted to present. The next one is Mandelbrot's tree. Mandelbrot's tree uses as base this figure, which then gets twisted and reduced and produced symmetrically. Here is the program. The program is pretty large because it has a lot of vertices, as you can see. 1, 2, 3, 4, 5, 6, 7, 8 vertices, and so you need to take care of those 8 vertices and reduce the figure accordingly. And so these references are for from basic, and I was able to translate that. That's for p equal 2, which is the second level, p equal 3, and you see how that tree starts building up. I do have to report a bug in the program, and is that there is a missing line here in every step, but I think I'm capturing the basic structure of the tree. And this is Mandelbrot tree. It's kind of a mathematical tree, but it does have that self-similarity appropriate of fractals. For 7, this is a picture I took. For 8, you can see how much more of the tree gets completed. 9, and we're able to get to 10 with that basis. I put this in a drafting software and color the tree in black, and it looks more impressive. And you can see that shape repeated at different levels, and the tree basically filling up the plane, which are characteristics of fractals. So this is the third example of fractals, the second of fractal trees. And the final example I wanted to show you is a fractal star. This is in Lauder's book, page 75, figure 424. And this one has 4 parameters. The level of the fractal, the number of vertices of the basic structure that we're going to use, an angle, and a radial distance. For p equals 0, we have nothing basically. For p equals 1, then we get a 5-star, a 5-point star. P equal 2, then the star starts having stars attached to it. For p equals 3, we can see how the main star is there, the stars and the points of that star are there, and then you get stars in the tips of that smaller star. For p equals 4, is to getting another level of stars, but there is self-similarity to the figure. And for p equals 5, you get this nice picture. Now I have these are screenshots I took because it takes a while to produce in the coordinates of all the points that define the stars at the different levels. This is another case for v equals 3. If I put p equal 2, or even start with p equal 1, you start getting, rather than a star, you start getting like squares. P equal 2, p equal 3, 4, and start getting taking longer to produce the results because there are more and more data points to carry over. I'm going to pause here and show you the result. It actually didn't take that long. But I have here the case for p equals 6, which was the next level. That takes a much longer time. And it's based on the same program, but now we have a v equals 3, which produces squares. And so you get the squares upon squares upon squares in self-similarity. The same idea of stars upon stars in here. I also try for b equals 5 and then a equals 120, and I get this sort of triangular shape. I try different values here, and you start getting some repetition, but there's not symmetry anymore. Again, all these files for the rectangular star, the 5-point stars, the Mandelbrot tree, the Pythagorean tree, and for swirling, or whirling, sorry, are available for you to download in the site indicated in the description of the video. With that, we conclude this particular video about whirls, fractal trees, and fractal stars.